In this video, we're going to officially introduce the concept of a polynomial function. We've seen two specific types of polynomial functions so far, linear functions and quadratic functions. In a linear function, the highest exponent on a variable is 1, and in a quadratic function, the highest exponent on a variable is 2. Now we're going to generalize what we've seen so far, focusing most specifically on what happens for exponents of 3 and up. Let's start by formally defining what a polynomial function is. A polynomial function is a function of the following form. So this looks a lot worse than it is. We're going to break this down into components and talk about what each of these individual pieces is. So let's start with the a's. Each a, notice we have several a's in this particular function description, each a is going to be a coefficient. So each a is going to be the coefficient for its respective term. So notice each of the a's has a subscript. The subscript tells us which exponent this goes with. So a sub n, our first coefficient, goes with the term where x has an exponent of n. Now keep in mind, when we have a real polynomial function, we're not going to have n's, we're going to have actual numbers. N is just in this case representing the highest exponent. But whenever we see a sub n, that means it's going to go with x to the nth power. So suppose, for instance, we see a sub 3. That means that's the coefficient that is going to go with the term where we have an x cubed. So every single a is going to be a coefficient, and when we have an actual polynomial function in an actual problem, all those a's are going to be actual constant numbers. So the highest exponent in our problem is called the degree of the polynomial. In this case, it's represented by the variable n. So the degree gives us a lot of information about the function. So when we have a linear function, the degree is going to be 1. When we have a quadratic function, the degree is going to be 2. And we can have degrees on up from there. So again, the degree gives us a lot of information about what the function's graph is going to be shaped like. So we focus on the degree more than anything. The term with the highest exponent, in other words, the term that gives us the degree, is called the leading term. So in this case, the leading term is represented as a sub n times x to the n power. And then specifically, the coefficient of this term is called the leading coefficient. So this is going to be a sub n. So when we write all our terms in order with our highest exponent first, the leading term with the leading coefficient is going to be the term we write first. It's going to be the term we write on the far left. And most of the information we're going to get about our polynomial function is going to come from this term specifically. So in general, what are we looking at? Well, we're looking at a bunch of variables. In this case, our variable is represented by x. Each variable has an exponent, and then each variable with its exponent has a coefficient. So in general, that's what we mean by a polynomial. It's a bunch of terms of that form, either added or subtracted from one another. Sometimes it helps to define what something is by explaining what it's not. So for an expression to be a polynomial, there cannot be several different things in the expression. In other words, for something to be a polynomial function, these are things we can't have in the function. One thing we can't have is fractional exponents. So something like x to the 1/2 power or x to the 1/3 power. We have a bunch of exponents, but every exponent has to be a positive whole number. Another thing we can't have is radicals of variables. So something like the square root of x or the cube root of x. These are actually directly related to fractional exponents. They're interchangeable. So anytime we have a variable, we can't have it inside of a radical. Again, it can only have an exponent. The exponent has to be a whole number. Another thing we can't have is variables in a denominator. So 1 over x, or this also corresponds to negative exponents. So anytime we raise something to a negative exponent, that would be the same thing as moving the variable to a denominator. So no variables in denominators, no variables in radicals, and then any exponent we have has to be a positive whole number. Another thing we can't have in a polynomial is absolute value. So that's something else we've looked at so far, expressions that have absolute value. Absolute value is also not considered to be polynomial. So anything that has absolute value in it, even if the rest of the function would be considered polynomial, having that absolute value in it makes it non-polynomial. The graph of a polynomial specifically is what we're interested in. And the graph of a polynomial is said to be smooth and continuous. So smooth just means there's no corners, there's no sharp corners, there's no points on the graph essentially. And then continuous means there's no break. So essentially, if we want to graph a polynomial function, it's going to be something that we could graph smoothly without lifting our pencil. So if we were to plan far enough ahead and have a sense of what the shape should look like, if it's polynomial, that means we can graph it completely without lifting a pencil. So let's look at some examples of graphs that do and do not represent polynomial functions. So this first graph is an example of a polynomial graph. Notice it's smooth, there's no sharp corners, and it's continuous. There's no break in the graph. So if we were to plan ahead for where all our intercepts are, for where we're going to start and where we're going to end, we could graph this graph completely without lifting a pencil and without drawing any corners. This next graph is an example of something that's not a polynomial function. You probably recognize this graph as the graph of the absolute value parent function. Although this graph is continuous, there's no holes in the graph, there is a corner on the graph, so this is not a smooth graph. So it fits one of the characteristics of a polynomial function, it doesn't fit the other, so this graph does not represent a polynomial function. Let's look at another one. So this graph is polynomial, again, smooth and continuous. We could draw this without lifting a pencil and without drawing any corners. This graph, although it's smooth, there's no corners, it's not continuous. There's a break in the graph, so we have two pieces on our graph. So all of our piecewise defined functions, which you may remember from before, piecewise defined functions have separate rules defined for different portions of the domain, and typically they have graphs that have some holes in them. Those particular functions do not define something that's polynomial. So even if the individual rules are polynomial individually, because when we graph them they end up having breaks across the domain, that means that those don't represent polynomial functions as a whole. So again, anytime we graph something that is considered to be polynomial, the graph is going to be smooth, there's not going to be any corners, and it's also going to be continuous, which means there aren't going to be any holes, there aren't going to be any breaks in the graph. So our goal at this point is to generate these polynomial graphs from our functions. What do we need to actually generate these graphs? Well, we're actually going to look at two different things that give us essentially what we need for a graph. The two things are called end behavior and zeros. So we're going to focus on each of these two things individually. Once we put these two components together, we essentially have enough to graph any polynomial function we want. The first attribute of polynomial graphs and polynomial functions we're going to look at is called end behavior. So end behavior describes the general direction the function follows as x goes to infinity and negative infinity. In other words, as we go to the left and the right on the graph, what's the graph of the function doing? Another way to think of this is which way are the arrows pointing, and that may be most helpful for when we actually need to graph. We know there's going to be tails going in either direction on the graph. We want to know which way are the tails pointing. So we determine this using what we call the leading term test. So our end behavior can be determined entirely from that leading term for our polynomial. So remember, the leading term is the term that has the highest exponent. If we were to write our terms in descending order with the highest exponent first, it would be that term out front that has the highest exponent. So we're going to look at two parts of the leading term. We're going to look at the leading coefficient, and we're going to look at the degree, in other words, the exponent that's on the leading term. So first, determine the degree. In other words, is it even or odd? We have a certain situation when the degree is even, so when our highest exponent is a 2, a 4, a 6, etc. And then we have certain things that happen when the degree is odd, so if it's a 3 or a 5 or a 7, so on and so forth. So determine the degree, is it even or odd? Second, determine the sign of the leading coefficient. So is it positive or negative? So if you put all this together, we've got 4 different situations. The degree can be even, and then the leading coefficient is either positive or negative. And then the degree can be odd, and then the leading coefficient is either positive or negative. So we're going to cover each of these 4 cases. These are the only 4 possibilities we have for combining these two components. So they give us all the different combinations of how our arrows could be pointing on the tails of our graph. So we're going to summarize all of this in a table. This table gives us all four combinations for our degree and for our leading coefficient, and it tells us based on what combination we're under, what's going to happen with the tails on the graph, what our end behavior is going to be. So let's start on the left. So suppose our degree is even and our leading coefficient is positive. In this case, both of our tails are going to be pointing upward. Now this doesn't give us any information about what happens in between the tails. All it tells us is which way the arrows are pointing when we start to fall off the graph. So underneath each of the orientations, we have several different ways of describing what this means. So underneath our arrows, we have some stuff with x's and infinities. This would be considered the most algebraically proper way to state the end behavior. If you're planning on continuing in math and you end up in calculus at some point, you'll see a lot of notation like this in calculus with the arrow. So the arrow is read as goes to. So in other words, as x goes to infinity, f of x goes to infinity. So that's a nice way of saying as our x values get really, really big in the positive direction, our y values also get really, really big in the positive direction. And then as x goes to negative infinity, f of x also goes to infinity. So as our x values get really, really big in the negative direction, our y values get really, really big in the positive direction. If we want to describe this in words, our graph is rising to the left and it's rising to the right. Now the way I like to remember this is I like to remember it based on a graph that I know really well. I know its end behavior, it's going to look like that particular graph. So if the degree is even and the leading coefficient is positive, the tails on our particular graph in question are going to look like the tails on the graph of x squared, the quadratic parent function. So any of these three ways equally describes what's happening with our end behavior. You honestly just need to use whichever one makes most sense to you, whichever one's easiest for you to remember. So anytime you see even degree, in other words, highest exponent of 2, 4, 6, so on, and your leading coefficient, the coefficient out front is positive, this is what your graph is going to look like on the tails of the graph. Our next possibility, suppose the degree is even but the leading coefficient is negative. Well, our arrows are pointing in the same way, but now they're pointing down. So we're falling to the left and we're falling to the right. And in this case, it's going to look like f of x equals negative x squared. So that would be the quadratic parent function, but remember having that negative out front gives us a vertical reflection. So the arrows on the quadratic parent function point upward. If we put a negative out front, that means the arrows flip downward, so they're both pointing downward. So anytime the degree is even, the arrows are going to be pointing in the same direction, and then the leading coefficient tells you whether or not they're going to be pointing upward or if they're going to be pointing downward. Now what happens if the degree is odd? So suppose the degree is odd and then the leading coefficient is positive. Anytime the degree is odd, the arrows are going to be pointing in opposite directions. So if the degree is odd and the leading coefficient is positive, we're falling to the left and we're rising to the right. In other words, the tails of our graph are going to look like the tails of the graph on the cubic parent function. So if you remember what that graph looks like, it looks kind of like a squiggle that goes through the origin. So it's an increasing function. It starts at negative infinity, and then it goes toward positive infinity vertically. So the tails point down to the left and up to the right. So this is if our degree is odd and our leading coefficient is positive. If our degree is odd and the leading coefficient is negative, we're rising left and falling right. In other words, it looks like the negative or the reflection, the vertical reflection of our cubic parent function. So our left tail is pointing upward and our right tail is pointing downward. So these are our four cases. These are the only possibilities we have. Either both tails are pointing in the same direction or both tails are pointing in an opposite direction. And then in each of these cases, we have two subcases. So again, remember the way of writing this that makes most sense to you. The most important part, of course, is can you put it on a graph? Do you recognize where the tails are going to be pointing? So that's why it helps me to think of it in terms of the parent graphs. Which parent graph is this going to look like? Now again, just to reiterate, All this tells us is where the arrows are pointing. It doesn't tell us anything about what happens in between those arrows. We're going to need more information to determine that, and that's actually what we're going to look at next. But first, let's try a few examples of end behavior. Based on the function, how do we determine what the end behavior is going to be? So let's determine the end behavior of this particular polynomial function. So f of x is equal to negative 4x to the fifth plus 6x to the fourth minus 2x. So we're going to use the leading term test here. We need to identify the leading term, and then we're going to base the end behavior of this particular function on whatever the leading term tells us. So first thing we need to do is we need to make sure that we're actually listing our terms in the correct order. It's possible that you may be given a polynomial function where the terms are out of order. So before you do anything, before you try to determine the leading term, make sure all your terms are in descending order by the exponent. So in this case, we have an exponent of 5, an exponent of 4, and then an exponent with an understood 1. So our terms are written in order, so we can immediately identify our leading term as negative 4x to the fifth. So in this case, we have an odd degree. Our degree is 5. We have an odd degree. And our leading coefficient is negative. So if I have an odd degree, it means my tails are going to be pointing in opposite directions. It's going to look like the x cubed graph. However, if we have a negative leading coefficient, that means we're taking what we have in the x cubed graph and we're flipping it upside down. So if the x cubed graph is falling to the left and rising to the right, once we put that negative leading coefficient out there, it means it's rising to the left and falling to the right. So our end behavior has a tail pointing upward on the left and a tail pointing downward on the right. Let's try another one. So notice this particular polynomial function looks a little different than the ones we've seen before. That's because this particular polynomial function has been factored. Now just because it doesn't look like our initial form doesn't mean it's not polynomial. Remember, the requirement for a polynomial was we have a variable, we can have coefficients, we can have exponents as long as the exponents are positive whole numbers. And both of those criteria are satisfied here. So this is a polynomial function, but it's not in an expanded form. It's in a factored form. Now, as we're going to see in a little bit, it may actually help us from time to time to have a function that's in factored form. But for purposes of finding the leading term, we have a problem. So because this function is in factored form, we can't immediately determine the leading term. We have factors, not terms. So if we want the leading term, conceptually, we'd have to take all of these factors and multiply everything back out, completely distribute this whole problem so that we could then find the term that has the highest exponent. Initially, it looks like the highest exponent is going to be 3, but if you think conceptually about what this would look like once we multiply everything out, we may have exponents that are going to be higher than 3. So in its form right now, we can't actually determine the leading term. The good news is we don't have to take all the time that it would take to multiply all of this out. This could take us 20 minutes to multiply all the way out correctly. And unfortunately, you do not have to do that. So all we need to do is we need to multiply the leading term from each factor. Essentially what we're going to do is we're going to take a shortcut to generate the leading term without having to take all the time that it would take to multiply this whole factored form out and get it into an expanded form. So how do we determine the leading term from each factor? Well, we identify each x. Notice we have 3 x's in this particular function. So the leading term is going to keep each x. It's going to keep the coefficient for that x, and then it's going to keep the exponent that goes with that x, or potentially goes with the x and the coefficient. So once we take all those x's, all their coefficients, and all their exponents, we're just going to multiply those together. And once we multiply each of those pieces together, that's going to give us the leading term for the whole polynomial. So let's see what that looks like. So our leading term is going to have 1/4 times x. So we've got an x, that's its coefficient, and there's an understood exponent of 1 on this x, so we don't need to write that. So 1/4 times x, that's the first group in our leading term. Once I go to the next factor, which is 2x minus 3, I need to keep that x. I keep its coefficient, which is 2 in this case. And notice that the entire factor is being cubed, so I have to keep that exponent, but it's applying both to the 2 and to the x. So when I write it in my leading term, I have to cube the 2 and I have to cube the x. So be careful there. The same thing applies for the next factor, which is 4 minus x. I have my x. Notice here the x has a leading coefficient of -1. It's kind of written out of order, but because there's a subtraction sign in front of the x, there's an understood -1 in front of that x. So I have to keep that negative sign in front of the x as its leading coefficient. And then both the negative and the x are being squared, so I keep the exponent, but I have to apply it to both. So those are the individual components that are going to make up our leading term. If we were to take all the time we needed to completely multiply out this polynomial, these are the individual pieces that would actually lead to our leading term. So once we multiply all these out, we have the leading term. So first thing we need to do is apply those exponents. So we apply the exponents. Notice the exponent has to distribute for the second two parts. So it ends up being 8x cubed. And when we square that negative x, that becomes a positive x squared. Now we can combine the numeric constant parts, and we can combine the variables with their exponents together. And we end up with 2 times x to the 6th power. So that is our leading term. Without having to do all the work to multiply everything out, that is our leading term if we were to distribute everything and write it in an expanded form. So in this case, we have an even degree and we have a positive leading coefficient. So if there's an even degree, that means the tails are going to be pointing in the same direction. So it's going to look like the x squared graph. Since our leading coefficient is positive, there's no reflection. So that means both our tails are going to be pointing upward on this graph. So we know how to determine where the tails are pointing. We determine this based on the leading term test, and we call the result of the leading term test the end behavior of the graph. But how do we know what happens in the middle? Well, that's what we're about to talk about. Let's talk about what a zero is and then finding the multiplicity of a zero. So a zero, otherwise known as a root of a polynomial function, is a value that solves the equation f of x is equal to 0. So this equation may look familiar. We've actually solved this equation several times for different functions we've looked at. The reason this looks familiar is because zeros, the solutions to this equation, correspond to x-intercepts on the graph of the function. X-intercepts essentially are what we're going to think of as what happens between the tails. Between the tails, the most we can really determine is where our intercepts lie. So we determine our end behavior and we determine our x-intercepts, and we've essentially got the major components of any graph. So what do we mean by multiplicity then? Our zeros represent x-intercepts. What do we mean by multiplicity? Well, when a polynomial function is factored, which is typically what we have to do to solve something of the form f of x is equal to 0, the multiplicity of each zero is going to be the exponent that goes with that zero's factor. And why do we care about this? Well, a zero's multiplicity tells you what happens at that x-intercept. We actually have two possibilities for what our graph is going to look like anytime we cross the x-axis. So here are two possibilities. We can either cross the x-axis, or it's also possible that we just touch it and we bounce back. The way we determine what's going to happen at a specific x-intercept is based on the multiplicity. It's based on the exponent we have for that particular factor that gives us that particular x-intercept. So if we have an odd multiplicity, in other words, an understood exponent of 1, or an exponent of 3 or 5, etc., the graph is going to cross the x-axis. So how we're actually oriented when we cross, either we're increasing or we're decreasing, that's really going to depend on other components that come together in the graph. So that particular part, how we're oriented, increasing or decreasing, we can't really determine until we start to put things together. But as long as we know we're crossing, we're halfway there. So we worry about orientation later. We want to know we are crossing, so we know essentially what we need to do when we graph. If instead we have an even multiplicity, so we have an exponent of 2, an exponent of 4, an exponent of 6, etc., we're going to touch the x-axis, then as opposed to crossing over and going from positive to negative, or from negative to positive, we're actually going to bounce back and go in the same direction we came from. So it actually looks like a little baby x squared graph on the x-axis. That's actually how I help myself remember this. So if it's an even multiplicity, it looks like that graph with an even degree. It looks like two tails pointing in the same direction. So it looks like a little baby x squared graph on our x-axis. So once we have our end behavior, where our tails are pointing, and once we have our zeros, in other words, what's happening between those tails, we essentially have enough to put together and give a fairly accurate graph of our polynomial function. So when we graph our polynomial function, we're going to follow 4 basic steps each time. So step 1 is to determine the function's end behavior. So we apply the leading term test, we determine where are the arrows pointing. Step 2 is to find the x-intercepts and their multiplicities. So we take the function, set it equal to 0, solve for all of our x's, look for the exponent that goes with each factor, and then we combine that to determine where are we crossing the x-axis and how are we crossing the x-axis. Step 3 is to find the y-intercept. There's always going to be exactly 1. So if you remember, in order to find a y-intercept, we let x be 0 and solve for the output that goes with that. Another way of saying that is we evaluate f of 0. So this just gives us one other point that we can put on our graph that gives us slightly more accuracy. And step 4 is just to put these components together and sketch the graph. So one thing I want you to keep in mind is that you need to just think big picture. Don't worry about what happens between these components. Although this gives us most of what we need for a graph, there are some things we're going to have to sweep under the rug just because we don't have enough math to deal with them yet. So as long as you know where the tails are pointing and in general what's happening in between with the intercepts, you have enough to get a reasonably accurate graph. So let's try our first example. So we want to sketch the graph of f of x is equal to 2 times x plus 4 times x minus 1 squared. So notice we have another polynomial function where everything is already factored for us. So this means finding the leading term, in other words, finding end behavior using the leading term test. That may be a little more involved, but chances are when we find the x-intercepts, that's going to be substantially easier than it could be. So first thing we want to do is determine the function's end behavior. Because we don't have terms, we have factors, we need to generate the leading term from the factored form. So our leading term has to have each coefficient, each x, and then each exponent that goes with the x. So notice that 2 out front, although it's not directly tied to an x, it is a coefficient for the whole problem, so we need to include it. The first factor has an x with an understood exponent of 1, so we don't need to write the exponent, we just write the x. And then our last factor, x minus 1, there's no specific coefficient written in front of the x, but the x is being squared, so we have to include the square on the x. So if we multiply all these pieces together, we end up with 2x cubed. So we have an odd degree and a positive leading coefficient. So that means in terms of our end behavior, we're going to be falling to the left, in other words, pointing down to the left, and rising right, or pointing up towards the right. Now let's find our zeros. So remember, to find our zeros, we're solving the equation f of x is equal to 0. So we're taking our rule for our function and setting it equal to 0 to solve for x. So this is already factored, so most of the work has been done for us. Notice the 2 out front is just multiplied, so I can just divide it from both sides and it completely goes away without affecting the zeros and without affecting the x-intercepts. So because this is already factored, I can just take each of these individual factors and set them equal to 0 and solve for x. So in our first factor, we get x equals negative 4. Well, the factor that x-intercept came from has an understood exponent of 1, which means the multiplicity of this x-intercept, of this 0, is going to be 1. Anytime we have an odd multiplicity, it means when we graph this x-intercept, it's going to cross the x-axis. So our graph is actually going to cross from one side of the x-axis to the other at this particular x-intercept. Now what about the other one? So we have x minus 1 squared is equal to 0. Well, if x minus 1 squared is equal to 0, then we know that x minus 1 itself has to also be 0. So we solve and we get the x-intercept, x equals 1. The factor that this one came from has an exponent of 2, which means that this intercept has a multiplicity of 2. Whenever we have an even multiplicity, it means we're going to just touch the x-axis, and then we're going to bounce back from the direction we came from. So we're going to touch and bounce back. In other words, if we're starting above the x-axis, we'll stay above. If we're starting from below the x-axis, we'll stay below. So until we put all these pieces together, we don't know officially whether we're going to be above, whether we're going to be below. That's all going to depend on how all the components fit together as a whole. The last thing we want to find is our y-intercept. So that's f of 0. If we let x be 0, we want to determine the output corresponding to an input of 0. So we plug in 0 in place of x, simplify using order of operations. So this ends up being a y-intercept of 8 once we simplify down using our order of operations. So we have our end behavior, we have our x-intercepts, and we have our y-intercept. So effectively, we have enough to generate a graph. So let's put all those individual pieces on a graph. So we know our end behavior is pointing down on the left-hand side and pointing up on the right-hand side. We found x-intercepts of -4 and 1, and we found a y-intercept of 8. So that's all the information we have about our graph. Anything past that, we would need to just plot extra points. So essentially what we're doing is we're now connecting the dots such that we abide by the end behavior that we know is required. So what I like to do for something like this is I like to just start from the left, start from my end behavior on the left, and just work my way from component to component to component until I get to the very end. So how do I know if I've graphed correctly? Well, once you get to the final x-intercept, you should already be pointing in the same direction as the right-hand end behavior. So let's go from left to right on this one. So we're starting below the x-axis on the left-hand side. My first x-intercept is at -4, and we decided we were going to have to cross the x-axis at -4. So I'm starting from the bottom left-hand corner, and I cross the x-axis at -4. Now here's where we're kind of sweeping things under the rug. So I know if I cross the x-axis but I have another x-intercept, at some point I'm going to have to loop back around. Otherwise, I'm just going to continue up to positive infinity and I'm never going to reach my other intercepts. What I don't know is exactly where I loop around. And unfortunately, at this point, we don't actually know enough math to figure that out exactly. So that's where you can kind of fake it. As long as you cross all your intercepts where you need to cross them, what happens in the middle, I'm not too concerned with. So we don't know exactly where we peak and turn around. That's up for you to decide. Just do your best. So we cross -4. We know we have a y-intercept that we need to pass through. And then we keep going down and our next x-intercept is at x equals 1. Well, we decided since that particular intercept has an even multiplicity, once we get to that intercept, we're going to touch the graph at the x-axis, and then we're just going to bounce back. So we come back in the same direction. So we're starting from above the x-axis. We're going to bounce back so that we're still above the x-axis. And sure enough, if we follow all of those steps, once we finish our last x-intercept, we're pointing in the correct direction. Our end behavior told us we need to be finished pointing upward. So as long as we bounce back from the positive x-axis, that means we're following the correct end behavior. So if we put all this together, most accurately, we have a graph that looks like this. So notice that in between the first and second x-intercept, the graph leaves the coordinate plane. That's because the peak, in other words, where we peak and turn around to go back towards the x-axis, is really high. It falls off the coordinate plane, and we don't know exactly where it is. So for our purposes, we probably wouldn't graph it that high. We don't know how high it's going to be. Again, this is what we're kind of sweeping under the rug because we don't have enough math to deal with that. As long as we deal with our intercepts correctly, we're going to consider it an accurate graph. This is also a great time to break out your graphing calculator. So if you want to make sure that you're graphing something like this as accurately as possible, try to graph it by hand first. Make sure you can identify all your intercepts, your multiplicity, your end behavior. Make sure you know how all the components are going to work together, and then use your graphing calculator to help you graph a little bit more accurately. Let's try one more. So now we want to sketch the graph of f of x is equal to the x to the 4th minus 4 times x squared. So we're in a different situation now. Now our polynomial is not pre-factored for us. So finding the leading term will be fast, but finding the zeros, finding the x-intercepts may take a little bit more work. So let's start with the end behavior. So we're looking for our leading term. Our terms are written in order, so our highest exponent is first, which means we can immediately identify the leading term from the function. So our leading term is going to be x to the fourth power. So our degree is even, which means our tails are pointing in the same direction. And our leading coefficient is an understood 1, so in this case it's going to be a positive number, which means that our tails are both going to be pointing upward. So our end behavior is upward to the left and upward to the right. Now we want to find our zeros. So we're solving the equation f of x is equal to 0. So we set our function rule equal to 0 and we're solving for x. Now again, we're not already factored, so our goal here is to factor. Anytime we see an equation that has exponents in it, immediately we need to think factoring in order to write individual factors that we can set equal to 0. So what I initially noticed with this one is that we have a common factor of x squared for each of the terms. So I can immediately pull out that greatest common factor and write what I'm left with. So I pull out an x squared and I'm left with x squared minus 4. After each step in factorization, I have to reevaluate what I'm left with. Can it still be factored? Well, x squared minus 4 is a special case of factoring that we call a difference of squares. So this part also factors into 2 more factors. So we've got our x squared up front, and then x squared minus 4 factors into x plus 2 and x minus 2. Again, that's a special case of factoring. If you need to review factoring, I've put some videos up that help you review some special cases for factoring. So it's worth your time to go back and look at those if this one wasn't obvious to you. So once everything is fully factored, we take each of our factors and then we set the individual factors equal to 0 and solve. So for our first factor, x squared is equal to 0, this means x is 0. And then of course the exponent on that factor is 2. So that means this intercept at x equals 0 has a multiplicity of 2. Since it's an even multiplicity, that means our graph is going to touch the x-axis and bounce back at this intercept. For our next factor, x plus 2, we solve and x is equal to negative 2. There's an understood exponent of negative 1 on this factor, which means our multiplicity is going to be 1 for this x-intercept. It's an odd multiplicity, so we're going to cross the x-axis at this particular x-intercept. And then our final factor, x minus 2, we solve for x, we get x is equal to positive 2. Again, we have a multiplicity of 1, so we're also going to cross the x-axis at this intercept. So the last thing we want to find is our y-intercept. We're solving f of 0. Well, in this case, when we solve f of 0, it turns out to be 0. So our y-intercept is at 0. Well, we actually found an x-intercept at 0 as well. Whenever we have an x-intercept at 0, the y-intercept is going to coincide with that. So we don't actually have an additional point that comes from the y-intercept. That's okay. We have enough information to put everything together. So let's just add all those pieces to our graph. So we know that we're rising on the left, and we're also rising on the right. Our end behavior tells us that our tails are going to be pointing in the same direction, and in this case, they're going to be pointing upward. We have x-intercepts at negative 2, 0, and positive 2. And we decided we're going to cross the x-axis at negative 2 and positive 2, and we're going to touch the x-axis and bounce back at x equals 0. So if I'm starting from the left-hand side and just following through each of the components in order to get to the right-hand side of the graph, I'm starting from the upper left-hand corner. I cross the x-axis at negative 2. Now I know I have another x-intercept, so at some point I have to loop around. Again, as mentioned before, we don't know exactly where we loop around, we just know we have to loop around at some point. So we have to dip down and loop back around in order to get back to x equals 0. Well, we know that at this particular intercept, we're not going to cross. We're just going to touch and bounce back. So when we get to x equals 0, we're below the x-axis. We're going to stay below the x-axis and bounce back down. We know we need to cross at 2, so somewhere between x equals 0 and x equals 2, again, we have to loop back around to make our way back towards the x-axis. So at some unknown point, I loop around and change back towards the positive direction. I cross over at x equals 2, And then as long as I've done everything correctly, I should be pointing in the direction that my right-hand end behavior tells me I'm supposed to be pointing. In this case, the end behavior tells me I should be pointing upwards once I cross over the last intercept. And sure enough, if we followed everything correctly, that is the way we're pointing. So if I put all these pieces together, I get a graph that looks roughly like this. And again, to get a better sense of what this graph looks like in order to find some more points, if you want a slightly more accurate graph, this is a great time to use your graphing calculator. Put this into the graphing utility. You can use the table function, and that'll give you some additional points that'll give you an even better graph than the one you've got now. So let's summarize what we learned about polynomial functions in this video, specifically about graphing polynomial functions. So a polynomial function's graph is generally defined by its end behavior and by its intercepts. So those are the components we focus on finding in order to generate a graph of the function that we're given. So end behavior specifically, in other words, where the arrows are pointing on the tails of the graph, that's determined using the leading term test. So we determine the degree of the polynomial, in other words, what's the exponent on the leading term. And then is the leading coefficient, the coefficient on that particular term, is it positive or negative? So that gives us 4 different possible combinations. Whichever one we fall under will determine which way our arrows are pointing for our graph. The next thing we care about is our x-intercepts, in other words, our zeros. This is typically going to be the most complicated thing to find for our function, and as our function gets more complicated, finding the x-intercepts becomes a much more challenging thing to do. In general, though, finding x-intercepts is always done by solving the equation f of x is equal to 0. In other words, if we assume y is 0, we're finding the x values that make that equation true. And then behavior at the x-axis at those particular intercepts, we have 2 possibilities. We either cross the x-axis, going from positive to negative, or from negative to positive, or we can also touch and bounce back, which means we're starting from one side, either above or below the x-axis, and then we're just touching the x-axis and then turning around and going back where we came from. This is determined by the multiplicity of each of the intercepts. So once we solve our equation, f of x is equal to 0, by factoring, the multiplicity is going to be the exponent on the factor that gave us that particular x-intercept. And whether that multiplicity is even or odd is going to tell us whether we cross or whether we touch and bounce back. And finally, we can find our y-intercept. It's always found the same way, by evaluating f of 0. So putting all these pieces together, we get a general sense of what our graph looks like. There are certain things we can't determine about our graph, but as long as we know where our tails are pointing and what's happening in general in between those tails, we have a fairly accurate graph.